Quantum mechanics is a fundamental theory in physics that describes the behavior of particles at the atomic and subatomic levels. It challenges our classical understanding of the physical world and introduces concepts that are both fascinating and perplexing. Developed in the early 20th century, quantum mechanics has revolutionized our understanding of nature and has led to numerous technological advancements. This video explores the key principles of quantum mechanics, significant experiments, practical applications, and its philosophical implications. Fundamental principles: wave-particle duality. One of the most intriguing aspects of quantum mechanics is wave-particle duality. This principle states that particles, such as electrons and photons, exhibit both wave-like and particle-like properties. The double-slit experiment is a classic demonstration of this duality. When particles pass through two slits, they create an interference pattern on a screen, characteristic of waves. However, when observed, they behave like particles, hitting the screen at specific points. Superposition. Superposition is another cornerstone of quantum mechanics. It posits that particles can exist in multiple states simultaneously until measured. This principle is famously illustrated by Schrödinger's cat thought experiment, where a cat in a sealed box is simultaneously alive and dead until the box is opened and observed. Superposition is crucial for the functioning of quantum computers, which can perform multiple calculations at once. Entanglement. Quantum entanglement describes a phenomenon where particles become interconnected in such a way that the state of one particle instantaneously influences the state of another, regardless of the distance between them. This spooky action at a distance, as Einstein called it, has been experimentally verified and is a key resource for quantum communication and cryptography. Uncertainty principle. Heisenberg's uncertainty principle is a fundamental limit on the precision with which certain pairs of properties, such as position and momentum, can be simultaneously known. The more precisely one property is measured, the less precisely the other can be known. This principle highlights the inherent limitations of our ability to predict the behavior of quantum systems with absolute certainty. Key experiments and discoveries. Double-slit experiment. The double-slit experiment, first performed by Thomas Young in 1801, was later adapted to demonstrate the wave-particle duality of electrons. When electrons are fired through two closely spaced slits, they produce an interference pattern on a detection screen, indicating wave-like behavior. However, when detectors are placed at the slits to observe which slit the electrons pass through, the interference pattern disappears, and the electrons behave like particles. Photoelectric effect. Albert Einstein's explanation of the photoelectric effect in 1905 provided crucial evidence for the quantization of light. He proposed that light consists of discrete packets of energy called photons. When light shines on a metal surface, it ejects electrons from the surface if the photons have sufficient energy. This discovery earned Einstein the Nobel Prize in Physics and laid the foundation for quantum theory. Bell's theorem and experiments. John Bell's theorem, formulated in 1964, provided a way to test the predictions of quantum mechanics against classical physics. Bell's experiments, conducted in the 1980s, demonstrated that the correlations predicted by quantum mechanics for entangled particles could not be explained by any local hidden variable theory. These experiments confirmed the non-local nature of quantum entanglement and solidified the validity of quantum mechanics. Applications of quantum mechanics. Quantum computing. Quantum computing leverages the principles of superposition and entanglement to perform computations that are infeasible for classical computers. Quantum bits, or qubits, can represent both 0 and 1 simultaneously, allowing quantum computers to process vast amounts of data in parallel. This has the potential to revolutionize fields such as cryptography, optimization, and drug discovery. Quantum cryptography. Quantum cryptography uses the principles of quantum mechanics to create secure communication systems. Quantum key distribution, QKD, allows two parties to share a secret key with guaranteed security, as any attempt to eavesdrop on the key exchange would disturb the quantum states and be detected. This technology promises unbreakable encryption methods for secure communication. Medical imaging quantum mechanics has also contributed to advancements in medical imaging technologies. Magnetic resonance imaging, MRI, relies on the principles of nuclear magnetic resonance, a quantum mechanical phenomenon, to produce detailed images of the human body's internal structures. This non-invasive technique has become a crucial tool in medical diagnostics. Philosophical implications, nature of reality. Quantum mechanics challenges classical notions of reality and determinism. The probabilistic nature of quantum mechanics suggests that particles do not have definite properties until measured. This raises profound questions about the nature of reality and whether the universe is fundamentally deterministic or probabilistic. Role of the observer. The role of the observer in quantum mechanics has been a topic of intense debate. The Copenhagen interpretation, one of the most widely accepted interpretations, posits that the act of measurement collapses a quantum system's wave function into a definite state. This implies that the observer plays a crucial role in determining the outcome of a quantum event, blurring the line between the observer and the observed. Conclusion: quantum mechanics has revolutionized our understanding of the physical world and has led to numerous technological advancements. Its fundamental principles, such as wave-particle duality, superposition, entanglement, and the uncertainty principle, challenge our classical intuitions and open up new possibilities for technology and philosophy. As research in quantum mechanics continues to advance, it promises to unlock even more mysteries of the subatomic world and reshape our understanding of reality.